Hey guys, it's Mr. Sanchez coming at you with another lesson for precalculus. I almost said algebra 2, guys. Almost said algebra 2, but it is precalculus. We are covering section 4.4, properties of rational functions, part 1. Okay, it's part 1 because we're not going to go over horizontal asymptotes. We'll do that in part 2. We're going to be going over how to graph 1 over x and 1 over x squared using some transformations. That's our first learning target. Our second learning target is find the domain of a rational function. Our third learning target is find vertical asymptotes of a rational function. All right. When it comes to graphing 1 over x, it's very easy. Here are some key points. -2, -1/2, that's right here. -1, -1, that's right here. -1/2, -2. So, and then that forms this part of the graph. This is called a branch. And then this other one right here is another branch. And that's another key point, 1/2, 2, 1, 1, 2, 1/2. Some key features about this graph is that it is symmetric with respect to the origin, as well as it has a horizontal asymptote of y equals 0. So that means that technically speaking, this graph should never touch the x-axis because it'll never reach it. That's what a horizontal asymptote means. It also says that we have a vertical asymptote at x equals 0. Yeah, vertical asymptote, so that means that our graph will never touch the y-axis either. We can get closer and closer, but we'll never end up touching it. This happens because we have a divide by 0 at x equals 0. So that's why. Next up, we have graph of y equals 1 over x squared, right? This is very similar to 1 over x, only slightly different. Our key points are -2, 1/4, -1, 1, -1/2, 4. And then it has symmetry with respect to the y-axis. So 1/2, 4, 1, 1, and 2, 4. 2, 1/4. Right. These are the other key points. What makes this graph special is that it also has a vertical asymptote at x equals 0, so it'll never touch. It doesn't not have a y-intercept, and it never has an x-intercept because it also has a horizontal asymptote. All right, those are the base functions. All right. Okay, and that's basically it. And next, we're going to apply some transformations to graph these. Okay, so let's go on to our next slide. Example, we're going to be using transformations to graph a rational function. Okay, so let's start over here. So we look at this rational function right here. The first thing you'll notice is that the parent function is 1 over x. Okay, and so we're going to go ahead and draw that parent function. Remember, it has vertical asymptote of x equals 0 and a horizontal asymptote of y equals 0. And then you just draw the key points. It's 0, 1, 1, 1/2, 2, and 2, 1/2. And you're going to go ahead and draw that. It has these points. And then you'll have -1, -1, -1/2, -2, and then -2, -1/2. Right, so that's the parent function. All right, and then what we're going to do is we're going to shift it to the, we're going to go ahead and perform this operation right here, which means shift to the right 2 spaces. Okay. So now we're going to graph 1 over x minus 2, right? So that what that means is that our vertical asymptote can move 2 spaces too. So if it was at 0, 0, it's not going to be at 2. At 2, x equals 2. All right, but a horizontal asymptote stays the same, y equals 0. And then we just shift those points over. So it's always going to be this point right here, this point right here, and this point right here. And boop. And right here and here. And boop. All right. That's that second step. That's shift left 2 spaces, shift right 2 spaces. That's wrong thing. Shift 2 units to the right. And the last step we're gonna notice is that we have this -1, so we're gonna shift 1 unit down. This means 1 unit down. It's 1 unit down from our last graph, so from this one right here. So, and the way we draw that is by shifting our horizontal asymptote. So our horizontal asymptote is going to go down by 1. Right? And so everything is shifted, and then you just draw the same key points. Right, and we go. Ta-da. And we're done with that. Okay, now we're gonna do the same thing with the second graph. Okay. With the second equation. So that's 1/1, and that's how we graph 1 over x minus 2 or minus 1. And now we're gonna graph 1 over x plus 2 squared minus 1. So the parent function here is 1 over x squared. So let's go ahead and graph that. That looks like this. Oops, not here. It goes here, here, and here. Right. So it's 1, -1, 1/2 comma 1/4, and then 2 comma 1/4. And that's our graph. And our asymptotes are like this. And that's our first graph, right? Next, we're gonna apply the horizontal shift. So we're gonna do 1 over x plus 2 squared. So that means 2 to the left. Right, so that means our horizontal asymptote moves over here. I mean our vertical asymptote. And then we're gonna draw the same graph. Trust me, this gets easier the more you do it. And we're gonna draw this like this. And we're gonna draw this like this, right? And that's our graph. And last but not least, the last step says +1. So now we're going to graph 1 over x plus 2 squared plus 1. So we're gonna move up 1 unit, right? Because it says +1. Just making sure. Yep, +1. So we have a vertical asymptote here. And then that means this is our vertical asymptote over here. And then we're just gonna do the same thing we've been doing. And this is our new graph. And that's it, guys. That's how you graph 1 over x plus 2 squared plus 1. All right. Next up, we're gonna do finding the domain of rational functions. All right. So this is the same thing as before. Oops, ignore my phone. Yeah, so we're gonna do x plus 5, you see? So remember, we still gonna make the denominator equal to 0. So cannot equal 0. So we have x plus 5 cannot equal 0. All right, and we're gonna do -5 here. And you're gonna get x cannot equal 5, -5. So that means that our domain is from -infinity to -5, union -5 to infinity. Similarly over here, so point number 2, like I said, these are just problems in which our denominator cannot equal to 0. That's about it. So we got x squared -4 equal to 0. We can find the zeros by factoring. So x plus 2, x minus 2 cannot equal 0. So that means x cannot equal 2, x cannot equal -2. So how do we write that inner notation? It's -infinity to -2, union -2 to 2, and union 2 to infinity. This next problem, when we look at x squared plus 1 cannot equal 0. Let's go try and solve it. -1, -1. So we're gonna get x squared cannot equal -1. If you take the square root of both sides, you get x cannot equal plus or minus I. Because we get an imaginary number, that means that this, technically speaking, x squared plus 1 can never equal 0. So therefore, this has this has the domain is all real numbers. That's all it means. And we like to write that like this. All right. Now, problem number 4 is kind of tricky because sometimes you can factor the top, right? You can factor the top to x plus 1 over x minus 1 all over x minus 1. And one thing you can notice is you might think, oh, I can cancel this out. This function is really equal to x plus 1. But then if you do that, this is the original function. So right here, this is simplified. And although it's simplified, that doesn't mean that x minus 1 is not in the denominator. So what that means is that we have x plus 1, but x minus 1, we still can't let the denominator equal to 0. So x cannot equal 1. So this is part of our equation. So it's this, but x cannot equal 1. Okay, so that's our domain. So it goes from negative infinity to positive 1, union positive 1 to infinity. Okay, and that's still our domain, or D. Right. Now, next up is our last four problem for this part 1. It's called vertical asymptotes. How do we find a vertical asymptotes? So surprisingly, it's very similar to finding the domain of a function. Where in the domain, we want to find out when the denominator does not equal 0. This time we want to find out when the denominator does equal to 0. Because when the denominator equals to 0, that's when we get a vertical asymptote, right? So this time we want x minus 1 to equal 0, right? Because that's the denominator. So that means that equals x equals 1. This right here is our vertical asymptote. Okay. Ta-da. Similarly, you're going to do the same thing for x squared minus 4. You're going to get x squared minus 4 cannot equals to 0. You're going to get x plus 2, x minus 2 equal to 0. And you're going to get x equals to negative 2 and x equals to 2. These here are our VAs, our vertical asymptotes. This one is x squared plus 1, as we went over in the last one. This can never equal to 0, so it has no vertical asymptotes. All right, because it has imaginary numbers. D is where we have an issue. You're gonna notice that these two, it's kind of hard to find out when these are equal to 0. Not really, but it is. What you're gonna notice is both the top and the bottom are factorable. So we need to factor both of them to find our zeros, right? So before we can find our vertical asymptotes, you gotta factor both the top and the bottom. And if you factor this correctly, you're gonna have x minus 3 and then x plus 4. No, not 4, 7. Okay. And then what happens is you're notice this x minus 3 cancels out this x minus 3. So when you have this when this occurs, that actually means this one here, not a vertical asymptote. It's actually a hole. Is a hole. It sounded like I said hole. And so x equals 3 is not a vertical asymptote. So then all we have to do is x plus 7 equals 0. And then you're gonna get x equals to negative 7. So this is our VA. Only this one, because the other one is a hole. All right, but that's basically it. If you need a video, I mean, if you need any more help or questions during class, feel free to ask me. We're gonna be going over this a lot, and we're gonna be doing the second half of this later on today. So hopefully you'll see it, or maybe whenever you see this video, the video will be up. All right, bye-bye.